Welcome everyone to section number 3, or welcome back really. In this video we're going to be talking about local mins and maxes, right? So our goal here is to find these things, these local mins and maxes for a function given to us via an equation, right? So if we are given a graph, then the claim is it's pretty easy to identify these things. It's hard though, or it's more difficult when we have an equation. Alright, so remember back in section number 1 of chapter 3, we defined these things critical numbers, and we saw that they were useful for finding where minimums and maximums can occur. But back then we were talking about absolute minimums and maximums. We would like to transition now into local mins and maxes, and we hope to actually use our first derivative to maybe help classify. If we have a critical number, is it a local min, is it a local max, maybe it's neither, right? So we're going to use the first derivative to help us classify these things. So first I want to help us notice something. I'd like us to sketch really quick a function that is increasing from, let's see, negative infinity to negative 1, and then again from 3 to infinity, and decreasing kind of in between there from negative 1 to 3. So I'm going to go ahead and draw out my graph here. Notice that there's kind of some interesting things happening maybe at negative 1 and at 3. So maybe emphasize those. And now maybe pause the video for 30 seconds, try to sketch out a function that's increasing on these intervals and decreasing on this one, and then we'll resume. All right, so increasing from negative infinity until negative 1. So that means we're going up, 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 something like this. And then at negative 1 to 3, we start decreasing. So maybe I'm going to level off a little bit, and then I'm going to start decreasing from negative 1 to 3. So something like this. And then at 3, we start increasing again. From 3 into infinity, we're increasing, so something like this. Okay, and the thing that I want us to notice, that when we make this transition, right, over here we're increasing, and then we are decreasing. When we make this transition from increasing to decreasing here at negative 1, notice that this is a local max. It's not an absolute max, right? Because over here it's going to continue increasing and it's going to get higher than this, but this is a local max. Likewise, when you transition at 3 from decreasing to increasing, you get a local min. So this right here is a local min. And this following theorem says essentially that this is not a coincidence, right? That this will always happen. So here we go, the first derivative test for classifying critical numbers. So suppose f of x is a function and c is a critical number of that function f. Then, if the derivative changes from positive to negative, at that critical number c, then f has a local, well, let's pause for a second. If it has a positive derivative, then it's increasing, and then it changes to negative. That means it's decreasing, right? So increasing to decreasing, that means there's going to be a local maximum at c. Likewise, if the derivative changes from negative to positive at that critical number c, then f has, well, again, if the derivative is negative, that means the function's decreasing. If the derivative's positive, that means that the function's increasing. So if it changes from decreasing to increasing, that means we have a local minimum. And then finally, if the derivative does not change sign, so that is, it goes from positive to positive or from negative to negative, right? There's no sign change. Then the claim is f has neither a local minimum nor a local maximum at c. So again, maybe a picture from this. So if you have the derivative is positive, so I'm going to go ahead and do a local max here. So if you have the derivative is positive, and then the derivative is negative, something like this. So again, f prime is greater than 0, and then f prime is less than 0. That means at your value c, right, C is a local max. Likewise, local min, if you have the derivative is negative, then you have the derivative is positive. F prime is less than 0 to f prime is greater than 0. Then at the C value, you have a local min. And then in this case, neither. If you go from positive, so f prime is greater than 0, and then at C, it is a critical number, right? So maybe the derivative is equal to 0, so maybe it kind of levels out here, but then it continues on, and it's still positive. So f prime is still greater than 0. Then you can see that this is neither a local minimum nor a local max. So at this C value right here, it's neither. Likewise, if you were decreasing up until C, so f prime is less than 0, and then you continue decreasing more, so the derivative was still less than 0, and you didn't have any change in the sign of the derivative, then again that C value here is still, it's neither, right? It's neither going to be a local minimum nor a local maximum. All right, so let's actually get some practice applying these things. So an example here, I'd like to consider the following functions, figure out on the intervals in which they're increasing and decreasing, and then find where we have local maximums and local minimums. All right, so increasing and decreasing, these have something to do with the derivative and if it's positive or negative, right? So okay, let's go ahead and find the derivative here. F prime of x, this is going to be 6x squared plus 6x minus 36. And in order to figure out maybe where it's increasing, decreasing, I'm interested in the sign of this thing, right? So when I'm interested in the sign of it, well, I need to kind of, first of all, figure out what are these potential crossing points, right? When is this undefined or when is it equal to 0? So looking at this, it's never going to be undefined because I don't have any fractions, so I can't divide by 0. I don't have any square roots, so I can't have, negative under the square root or anything like this. So my only hope for these potential crossing points is when we have the derivative equal to 0. And then it would just cross through the x-axis. So let's go ahead and solve this. Well, maybe first thing I notice, everything's divisible by 6. So if I divide through by 6 on both sides, well, this side becomes this, and then 0 divided by 6 is still just 0. And now hopefully I can factor this, right? So I think it's going to be maybe like x plus 3 and x minus 2. So this gives me these points x equaling 2 and x equaling negative 3. So these are our potential crossing points, so let's go ahead and put them on a nice number line here. So negative 3 and 2, and now we're going to choose test values in each one of these kind of intervals. So maybe here I would choose 0, here I might choose 3, here I might choose negative 4, but again, they can be any numbers. It's just they're test points in these intervals, so you could choose like negative 5 or negative 100 even, right? But I usually choose relatively nice things to plug back into my derivative. So okay, let's go ahead and plug these in. Maybe first one I'll do 0. So if I plug in 0 everywhere I see an x, I'm going to have 0 plus 0 minus 36. So this is going to be, well, less than 0. So right here we have a negative. Okay, how about if I plug in negative 4? So I'm going to have 6 times, oops, let me go ahead and switch this back to green here. 6 times negative 4 squared, that's going to be 16. And then let's see, plus 6 times negative 4, that would be negative 24, minus 36. So let's see, this is going to be 96 minus 24 minus 36. So that's going to be 96 minus, let's see, 60, I believe. And so we get 36, and again, the big thing is that this is positive. I don't care so much about that the number is 36, but more so that it's positive. Okay, and then finally, if I plug in something like 3. So if I plug in 3, again, I'm plugging this into my derivative here. A common mistake is that you plug it into the original function. We're trying to figure out if the if we're trying to figure out if the derivative is positive or negative, because that's what tells us something about increasing or decreasing. We don't care about so much right now if the function is positive or negative. So again, we're plugging these into the derivative. Okay, so 3. So let's see, 6 times 9 plus 6 times 3 minus 36. So that's going to be 54 plus 18 minus 36, which also happens to equal 36. And again, the big thing is that this is greater than 0. Okay, so we were asked to figure out when is it increasing and decreasing, and then we want to find where are the local maximums or local minimums. So okay, let's say f is increasing on negative infinity all the way up to negative 3, and then again from 2 to infinity. F is decreasing on negative 3 to 2. F has a local max at x equals what? Negative 3, right? Because that's where it switches from positive derivative to negative derivative. That is, our function was increasing, it had a positive derivative, then it was decreasing, it had a negative derivative. So therefore, the shape that we're making here is a maximum. So it has a local max at negative 3, and f has a local min at x equals 2. Because there we switch from decreasing, right? So the derivative's negative, so the function's decreasing, to increasing. All right, and that right there is our final answer. Again, you can plug this into Desmos if you'd like to kind of sketch it out and verify that these are all correct. Okay, I have one more example for you. I'd like you to go ahead and maybe pause the video, try to get as far as you can. Again, same sort of questions. Where is it increasing, decreasing? Where are the local minimums? Where are the local maximums? So pause the video, get as far as you can on this one, and then you can unpause it and I'll spoil the surprise. All right, let's check in and see how you're doing here. I went ahead and calculated out the derivative. Remember, we have a quotient of functions, right? So we have to use the quotient rule here. So the derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the bottom squared. And now I went ahead, I distributed that 1, and I distributed the x, and then I simplified the top. Right? So 1 minus x squared is what I got in the top. Now the way that you get these potential crossing points, right, we're going to map these on a number line over here, is where either it's undefined, right, that would give us a vertical asymptote, and that's one way you can kind of potentially jump from positives to negatives or vice versa, or if it actually crosses through the x-axis, that would make it equal to 0. So okay, let's figure out where the denominator is equal to 0. And you can see I take the square root, I move things over, I take the square root again, but this is a not real answer, right? This would be the square root of -1. We know that's not real, it's I, right? It's an imaginary number. Okay, so we don't have to worry about this. There's no real number that you could plug in that would make this equal to 0. Now, how about where the numerator is equal to 0? That is where the entire thing is equal to 0. In this case, if you go ahead and solve, you can get x is equal to plus or minus 1. And so where I ended is what I graphed these on a number line again. Remember, we're interested in is the derivative here positive or negative. So I'm going to choose some test values and plug those into the derivative, figure out if it's positive or negative, because that will help me tell if the function is increasing or decreasing. Remember, increasing or decreasing has something to do if the derivative is positive or negative. So I'm going to go ahead and choose values like -2, 0, and 2. And plug those into my derivative function. Remember, this is my derivative down here. So maybe if I plugged in 0, that's usually a nice one. So if I plugged in 0, I would get 1 on top, and on bottom I would have 0 plus 1 squared, so 1 squared. And again, the big thing is that this is bigger than 0. So here we have positive. Now if I choose -2 and I plug it in, right? So I'm going to have 1 minus -2 squared. So -2 squared is going to be 4. -2 squared is going to be 4 plus 1 is going to be 5. And so this is going to be -3 over 25. Again, the big thing is that this is less than 0, and so we're going to have negative. Finally, if I chose if I choose 2 and plug it in. So if I choose 2 and plug it in, I'm going to get 1 minus 4 over 2 squared will be 4 plus 1 will be 5. And I've got to square all that. And so again, I get -3 over 25. This is less than 0. And so we have a negative. And therefore we have f is increasing on negative 1 to 1. Again, that's where the derivative is positive. F is decreasing on negative infinity all the way up to negative 1, then again from 1 to infinity. F has a local max at x equals, well, let's take a look here. If I'm going decreasing and then increasing, that's going to be a local min. Here I have increasing and then decreasing. That's going to be our local max. So that's going to be at x equals 1. And F has a local min at x equals negative 1. Again, right here. All right, and that is our final answer. In these problems, we saw that actually they always had a local minimum and a local maximum. This will not always be the case. We'll do a few problems in class where we see that this neither really does come up in problems that we will see in this course. All right, I'll see you guys next time.